Hello, everyone, and I think Jon is online. So if I get into too much trouble, he can come in and speak as well. So this is a presentation from all of us at Solemma. There, the slides are by Jon, and I'm just your narrator for today. I should also say that Solemma was started with one member who's no longer there, which is Kara, sitting back there. And we wouldn't have made it this far without her work in starting up the company. So thanks to her as well. So last year in Innsbruck, Jon presented this new kind of way of dealing with dynamic scene objects and radiance that we had created, which we call the multiverse. If you want details on that, we'll talk about it some today, but you can look back at the presentation from last year, which is nicely recorded and has like the slides and video. But the gist of it is that instead of kind of like binning photons to use a BSDF at the window interface, which is very useful, every time a photon or a ray intersects with a dynamic scene object like a roller blind or a Venetian blind, or a deciduous tree leaf, which might change color or like disappear entirely, we calculate like every possible interaction of that ray with all of the possible states, and trace that out. That's the multiversal idea. And since Jon's presentation, and since the release of ClimateStudio 2 about 2 or 3 weeks ago, this is all in our ClimateStudio interface and accessible by actual users, whereas last year it was just kind of like only on Jon's computer. I'll just go through some of the core changes and ideas here of implementing the multiversal method. One is that we now have dynamic materials. This is an example of the dynamic deciduous tree leaf material, which comes from some work that Jesse Pan and I presented at the Radiance Workshop in Toronto. Where basically you can choose different tree species and they will have a seasonality as to when like leaf fall versus growth versus color change, leaf growth versus full coverage versus color change versus leaf fall occurs. This is loosely based on climate data. And these can be mapped to a new library of tree objects, which we've implemented into ClimateStudio. So you can choose from 3 different leaf densities and 3 different tree shapes to give you like a 9-tree selection. This is loosely inspired by some of the work that Prigi and I did long ago. And these are high polygon trees at the moment, but there will be lower polygon options in the future. So when you choose one of these trees, you can also choose one of these dynamic leaf materials, and then you'll have a effectively deciduous tree in your simulation. Picking up from those types of materials on the tree leaves, you can also schedule basically any material dynamically. Snow cover is another one that's traditionally been kind of a little challenging to do in Radiance, which is implemented as like a core UI material in ClimateStudio. So you can create a little plane just above your green space ground plane if you're in a location that has significant snow cover. And there's a kind of quick and dirty algorithm of number of days below freezing, equivocating to some amount of snow accumulation, and then as it warms up, the snow cover will melt and less reflectance will be traced from the ground. This applies to this method applies to dynamic fenestration materials as well. So for example, here in the electrochromic glazing materials, rays that that hit the kind of EC glass geometry object in the scene can be selected along that ray path for changes in direct transmission effectively. We also still have BSDF representations of fabric shades, but we've extended the kind of 4 or 5 that were available by default in the original ClimateStudio, or the last version 1.9, to cover the entire LBNL complex glazing database fabric shade data. These fabric shades are measured using an integrating sphere, so they're not full goniofotometer measurements, but they're still quite useful for characterizing the shades. And one other like small thing for the Europeans out there is that all the shade materials are classified as per their EN 17037 glare reduction rating. So in the previous version, these were all controllable by the IES LM83 standard, which is pretty limiting. But now there are some more controls. There's a kind of hysteresis function where you can set that a user leaves the blinds down for a user controllable amount of time, like 2 hours, 4 hours, 2 days. However lazy you think, or however inactive you think your building users are, you can plug that in. And then there's also more kind of manual control options like depth of sunlight penetration that can be set in the user interface and used to control the operation of window shades. All of the BSDF materials from the complex glazing database can be simulated using an aperture BSDF or ABSDF type. But Jon has also ran polynomial fit functions against the BSDF data for both specular and diffuse transmission components. And these basically give you the same answers as the BSDF, but the benefit is that they're a bit faster to simulate because you end up skipping the lookup and the lookup process of the BSDF by translating them into a functional representation, which we put in via BRTD func. Jon noted that the BRTD func implementation for this is a slightly customized one because of how you have to deal with the diffuse portion. And then this kind of multiversal application can be arbitrarily applied to any material. So you can schedule the transparency or the geometry mesh face size scaling of any object in a ClimateStudio scene using a custom schedule. And a good example of where this might be useful is if you have like an awning or something that's deployed only at certain times of the year, like during the summer and not during the winter or something like that. So that shade device can be selectively in the simulation or out of it in any sort of climate-based annual calculation. So here's an example of a corner office simulated for the cold climate of Minneapolis with all of these dynamic scene elements in it. So it's a corner east and south facing office. So it's got an east facing glazing group and a south facing glazing group with dynamic fabric shades on them. There are two deciduous trees planted to the east. There is an awning on the south facade, and there's a large open ground space that can accumulate snow during the summer. So if you kind of look at all the dynamism of these elements, you've got tree leaves present for a portion of the year. You've got shades closed often in the morning on the east facade. You've got south shades closed in the winter months on the south facade. You have this awning that's deployed during 9 months out of the year when it's not snowing and cold. And you have the snow cover. You have the snow cover during the winter months. So if we just loop through this in ClimateStudio, when you have dynamic elements, when you run a point-in-time simulation, you'll get a visualization of them as well. So we can kind of see how these work throughout the year. So here we are in January, no leaves on the trees, snow cover, shades are largely down, the awning is away. And as we move forward, we can see the leaves growing into the trees, the awning coming out, the shades come up, although you can't see that in this visualization. The snow melts and we have grass. Eventually, the colors of the leaves start to change in the autumn. And I should maybe note that the color change has almost no effect on interior daylight levels as per the study we did in 2022, but it's It doesn't come with much simulation overhead, and it's nice to be able to visualize that. And then subsequently after the color change, you get the leaves starting to drop off a little slowly over the next couple of weeks. The shades come back down, and then snow cover begins to accumulate again. So that's kind of the impact of these things. We can look at this on an individualized basis as well. So these are now annual simulations. And this is just with the window shade dynamic elements. There's no trees, no dynamic snow cover in this scene. And we can see that there's a fair amount of, almost always these shades are closed in the morning, and you have like also shade closed on the south in the middle of the year without the awning present. And that gives us a SDA as per IES LM83 of about 58%. If we add in dynamic snow cover, so the ground reflectance changing, that increases the the daylight autonomy by about 4%. If that dynamic awning is added, you'll notice that the south shades are open much more during that period, or almost entirely during that period, because of the fixed shading element. That brings the spatial daylight autonomy up to 80% annually, because those shades are open instead of closed. And if you add the trees on the east facade, you'll also notice how those shades on the east facade are more open according to the LM83 2% rule. And it doesn't change the SDA that much, but it does change the view. So it gets us to about an 81% SDA. So these kind of dynamical scene elements can have a pretty big impact if you're designing with them in mind, like trees, awnings, etc. That's, we think this is a relatively novel thing. I think before you'd have to kind of brute force it a lot of the time to get, and composite illuminance files to get this together. Another thing that the multiverse allows is that it's a bit different than the 3 and 5 phase methods, where these kind of like window groups are like glow emitters in the calculation, and so they can't reflect light, really. They can only emit light effectively. And so with the multiverse, you can actually, and John talked about this last year, you can actually account for the kind of interreflections between like interior shades, pieces of glass, like in this illustration, a ray that might hit this closed blind and reflect back out the window. 3 and 5 phase might not catch that, but the multiverse can. And there's a question, I think, which is like, does this matter? And the answer is it can matter. In the case where your interior surfaces are low visible reflectance, in this case, like a 7% VLR glass and a 6% dark covered like fabric shade, the incremental daylight autonomy difference of having these reflections accounted for is pretty small. It's like 3% on the scale of this corner space, which is arguably, I think, not a very big impact. But if you really like highly reflective surfaces, in this case, a 80% white roller shade, and I don't know how common this would be, but a 31% VLR back face glass reflectance, these differences can accumulate pretty highly. So it can be up to 15% difference between not accounting for the interior reflections off of facade elements and accounting for them. So by default in ClimateStudio 2, these are turned on. They do have a slight calculation overhead, but you can also turn them off if you want to calculate without them. And it'll make things a little faster for you. I didn't cover this very clearly in the introduction, but the way the tree leaf growth works is not just like triggering the transparency of the leaves, but it has to do with the mesh vertex texture scaling effectively. So when leaves are full, the full geometry is accounted for as a surface that can reflect and intersect with rays. And then in these growth and drop periods, instead of randomly culling leaves, we just shrink the vertex coordinates that the multiverse counts as a location that a ray can interact with. And what this means is that, as these things shrink, there are certain potential rays that will be calculated, let's say like reflections off of a shrunken leaf here that theoretically would transmit through this leaf, but this will never happen because they always shrink at the same rate. And so there's some special code qualifications that have been implemented to drop these like potentially impossible to achieve multiversal states. And it's a little complicated, but like effectively what happens is in a forest of trees like this one, which Jon simulated to make this point, you drop something like more than 50% of the leaf-to-leaf interactions and a whole bunch of ray paths that end up speeding the calculation up by about 2 times. So these are just computational speed ups that have been implemented into the kind of multiversal process. The trees are an extreme situation because there's so many mesh faces for each leaf. If you're just doing this with roller blinds, it probably doesn't make that much of a difference. And this will be useful in the future for, this is not implemented yet, but eventually for Venetian blinds that might rotate in place. One thing you can already simulate these with multi-state VSDFs, like at different slight angles, but if you want to simulate the actual geometry, one beneficial thing is that, theoretically we can tell the ClimateStudio and Radiance engines that, all of these Venetian blinds are going to be at the same angle at the same time. So you don't need to, trace the relationships between this rotation angle and other ones that won't be present in that dynamic scene. So the other big, at least lighting side simulation lift that's happened in ClimateStudio 2.0 is that every simulation is multi-threaded on Windows. One thing I thought about is that we should probably benchmark this against the native Linux multi-threading, but we have not done that. In fact, we've only benchmarked against ourselves, which is a little lame, but nonetheless, so in 1.9, everything was a single thread for annual climate-based simulations. Renderings were always multi-threaded. But there's a combination of the multi-threading and some optimizations for how we're running the annual simulations that have led to relatively good speedups. These are benchmarked on an 8-core kind of like semi-performance laptop and a 16-core mid-tier Threadripper performance desktop with the GeForce 2080 Ti inside. And the simulation times for like a small office like this, using 7 ambient bounces and 4,000 ray samples per sensor point, dropped from about 28 seconds on our original version down to as low as 2.3 seconds for the performance desktop. So this is a small model. It's really fast at any rate. But when you get into bigger models, this goes from 7 to 10 minutes down to less than a minute, which is a pretty big improvement and will help like allow you to iterate through designs instead of waiting around for 10 minutes for simulation to finish. And even on gigantic models, we can't present this one because it's a private client model, but it's 400,000 square feet and 97,000 sensors with 174 dynamic shading elements. In CS 1.9, this took between 110 minutes on the laptop or 197 minutes on a single core of the Threadripper desktop. And on the 16 core, it gets down to about 10 minutes simulation time for the full quality calculation. So that's, it's a way to do these calculations relatively quickly without having to ship it off to like a cloud provider or something along those lines. These are just the speed up multipliers so you get up to around 14 times speed up for the large model on the performance desktop. And you can add more cores and this will get a little faster if you go to 32 or 64 cores, but there are diminishing returns as you add more cores. So if you add 64 cores, this multiplier won't go up by a factor of 4. It might go up to like 16 or 18 times faster, but that's just the nature of parallelization. Another thing, and this is mostly on the user interface side, is that we've been working a lot to improve electric lighting calculations. I'm not too long here. I think I'm okay. But we've been working a lot to improve electric lighting calculations. And one thing is that we're kind of creating automated luminaire fixture geometries where it makes sense to do so. It just helps add a sense of realism and renderings and even visualization within the user interface. So for example, if you have an IES file with a direct indirect kind of data source. So you've got like a large upward flux and a downward flux. Based on the fixture geometry in the IES file, it will automatically, CS will automatically create a little box for you, apply the upward flux geometry to the top of the box and the downward flux patterns to the bottom of the box. And this is something that IES-Terad doesn't natively do. So IES-Terad will handle this just fine, but it keeps these kind of direct and indirect fixtures on the same plane. And we've done a little bit of just optimization around some of IES-Terad's behavior. So if there's like kind of like spurious data in a IES measurement, like a small percentage of upward flux or sideways flux, less than 1% of the total lumens of the luminaire, we just get rid of that effectively in ClimateStudio, but IES-Terad will kind of like leave these like very tiny little flux surfaces up, which makes like the simulations take a bit longer. So that's just a kind of optimization function. Another thing that we've done is we've partnered with Pacific Northwest National Labs, PNNL, and they have this big database of spectral lamp power distribution measurements. So these are all integrated into ClimateStudio now. You can choose them. Right now, they're just for RGB rendering. So that'll get an accurate color perception across your RGB calculations. But thanks to Greg's great work with Radiance 6, thank you, Greg, the next step is to just turn on effectively full hyperspectral rendering based on this database. All of our glass materials in the default library also have like full spectral information, and all of our photopic reflective materials in the default database also have full spectral information because they come from my spectral measurement database. And so theoretically, we have when you build a normal ClimateStudio model, if you're not using custom materials, you're already building effectively a hyperspectral model. And so, look out in the future for this to just be an option to calculate. One other speed up that we've been undertaking with electric lighting is that there's a pretty significant overhead with IES-Terad when it looks up the data via source.cal. So if you have, what we're looking at here is on the left-hand side, there's just like a glow source lamp or glow source rendering, and on the right-hand side, there's IES-Terad. And it takes about 4 times longer to simulate that than just using like a simple glow material. Of course, you don't want to use just a simple glow material because you lose your luminaire distribution properties. So what we've done is we've kind of like just pre-computed all of the lookups at a relatively high resolution and just provide that instead of doing the lookup directly. And this gets speeds much closer to the kind of standard glow material rendering. So and pre-computation is on by default in ClimateStudio, but we're going from times of using the IES-Terad kind of process of 178 seconds to 69 seconds, about 2.6 or 2.8 speed up, or in a larger model, like a 3.0 speed up. So this is just enabling Radiance to handle large numbers of luminaires in a scene without having like a really big performance overhead. It's still not quite as fast as like a radiosity approach, as you might imagine, but you get like a much higher quality rendering out of it. So we're hoping to make the kind of Radiance workflow for electric lighting, more palatable to electric lighting designers. Oh, yeah, that's the last slide. There's no conclusion slide. But if anyone has any questions, I'm happy to answer. I think John's online, so he might answer. He might also have some clarifications that he's not happy with how I discussed. But anyone? Yeah. Oh, thank you. Mm-hmm. Yeah, so it interacts with that. So if you put a dynamic snow material over a PV collector surface in ClimateStudio with like a little bit of an offset, so the sensors stay under it, that will that will affect the result. You get into questions about like how are these things going to be maintained? Like, are they going to have snow cleaned off? In that case, you'd have to go into like a custom schedule, but you can absolutely do that. All the dynamic scene elements interact with the radiation calculations as well. Greg?
Great presentation. Related. One is the obvious thing where you're driving your simulation forward based on all patterns. Probably in many cases optimized. Really hard to flip that way.
John, are you here? Did you hear that? John can't hear it. Okay. I will, but can you speak just so I know if you're present? Otherwise, I'll take my shot at it.
Can you hear me?
Yeah. Yeah. Okay. Right. So I'll repeat the question. The question is, if you're looking for a set of control systems to optimize a certain lighting state, can the multiverse be used to kind of achieve that on an hour by hour basis, or does it need to be pre-scheduled based on predetermined data for everything?
Well, right now it needs to be pre-scheduled, sort of as an input. So last year I presented a couple of limited cases where you could kind of store all the paths in graphics memory and then kind of do real-time manipulations, but there's obviously a limit as to what you can store. So you either need a lot of graphics memory or you need kind of low sampling rates or things like that.
My second question too. Thanks, John.
Greg said no more questions.
Okay.
Anyone else? Right. Like alternative tone mapping methods. Yeah, beyond Pecan, not yet, but theoretically we could just apply other tone mappers to it. You should shoot me an email so I can put that into our like 800 GitHub issues for future development. Oh, okay, yeah. Well, I can bump it up to the top too. Oh yeah, David. There's not. That it's more causing more glare. Is that included in the like already show that the lazy users, whatever? Yeah, so that's a great question. And the answer is if you're calculating, let's say, an annual glare calculation in ClimateStudio, that will definitely raise the vertical luminance. But it doesn't really have any plausible way to interact with the blind scheduling algorithms right now. So actually, this is like one of those features that existed in our old software Diva that's not in ClimateStudio yet, was we used to have like a DGP-based control where you could say, okay, if you have a DGP over 0.35 or over 0.4, then close the blinds. But right now, most everything is still kind of like sensor-based illuminance, and so that part is missing, and it's something you just have to be a little cognizant of at the current moment. Yep. Mhm. That's a great question, and we've bounced this around like both. Like I'm also on the LM83 committee, which is perhaps a little awkward, but we've bounced this around both in the LM83 committee and at Solemma. So there was a question that LM83 dealt with, which is like, can blinds partially close to block off the direct sunlight? And of course, in reality, yes, they can. But in the simulation, the takeaway is pretty much like, no, they should always be fully open or fully closed. And that's just a decision to keep the algorithm like very describable in a certain sense. In certain places in Europe, I've learned that trees are explicitly not excluded from simulations because there are like light level requirements inside of housing developments, and there was a worry that, you know, if trees were keeping the certain amount of luminance from reaching the inside of homes, that developers might cut down the trees. And so there's all sorts of complications that you might think about with this. Like, my point of view is that simulating something realistic is generally good, and I don't have the exact answer right now as to, you know, should LEED calculations have a fixed ground plane reflectance, or should they have, you know, like only opaque trees? Like, maybe. And if that's the case, then in ClimateStudio, we would just flip that switch for LEED, which we already do. Like, you can't specify a custom occupancy schedule for a LEED calculation because it's codified in the metric. And so, you know, we'll follow whatever comes out, but for right now, these dynamic elements can be simulated accurately. And, you know, maybe people will game with it, but maybe that will lead them to planting nice trees around their buildings, and that might also be a good thing. Yeah, I mean, the ground reflectance is also like realistic if you put it in correctly, but of course someone could put in something like in an urban area that's not going to have accumulated snow cover, and then it's, you know, a little unfortunate. But I've probably gone too long. Thank you.